we shall discuss convergence or divergence of a series. So let's define a series. Suppose an is a sequence of real numbers, then an expression of the form a1 plus a2 plus a3 is called a series. It is denoted by summation an varies from 1 to infinity. If S1 represents the first term of series, S2 represents sum of first two terms of the series, S3 represents sum of first three terms, and so on. Sn is equal to a1 plus a2 plus an. Then Sn is called nth partial sum, and S1, S2, S3, S4, Sn is a sequence of partial sums obtained from the series summation an. Now, if this sequence of partial sums converges to some number s, then we say that the series summation an converges to s. And if the sequence of partial sums doesn't to a number, then we say the series is a divergent series. Recall that a sequence Sn converges to some real number S if for every given epsilon greater than 0 there exists a natural number m such that Sn minus S mod less than epsilon for all n greater than or equal to m. That is, if S1, S2, Sn are terms of the sequence, then there exists a stage, say mth stage. After that stage onward, all terms of the sequence lie in the epsilon neighborhood of point S. So this we know the definition of convergence of a sequence. So from definition of convergence of a sequence, we have defined what is meant by convergence of a series. So let's see two examples. So summation 1 over n into n plus 1. This is a series. So now first find its nth partial sum Sn. So you will notice that the nth partial sum is 1 minus 1 over n plus 1, and take its limit. Its limit is 1. So nth partial sum, the sequence of partial sums is convergent, and the sequence converges to 1. Therefore, this series also converges to 1. The second example is, let x is a real number between 0 and 1, then this geometric series has sum. We know Sn is 1 minus x power n plus 1 over 1 minus x. But if you take n very large, n tend to infinity, and x is less than 1, this term will tend to 0. So this infinite sum will converge to 1 over 1 minus x. So the from where we get the convergence of series? We get the convergence of series from the convergence of this sequence. So we know the limit of this sequence is 1 over 1 minus x. So convergence of sequence is implying the convergence of this series. Now we give a necessary condition for convergence of a series. So if summation an converges, then the sequence an will have limit 0. So this an is just replace summation from an and put commas. We get a1, a2, an, a sequence. It is not a sequence of partial sums. It is a sequence obtained by replacing plus plus sign by comma comma sign from a series. So the theorem is, if a series is convergent, then the corresponding sequence has limit 0. The proof is very easy. So take n plus 1th partial sum and delete Sn, the sum of n terms, we get just n plus 1th term. So now if you take limit both sides, the limit of Sn plus 1 is S, say, because the series is convergent, and we know a series convergent means the sequence of partial sums convergent. So this has limit S, this has limit S, it means S minus S 0. So this sequence an plus 1 has limit 0. So a convergent series give this sequence converges to 0. But the converse of this is not true. That is, if a sequence converges to 0, then the summation an may not converge. We shall see this in some examples. So consider this example. If mod x greater than or equal to 1 and summation xn is a series, this series is divergent, because if you see the limit of this thing, now x is greater than 1 and n is large, so x power n is very very large, so this number, so this the sequence will not tend to 0. So when the sequence is not tending to 0, it means this series cannot converge. We have seen in theorem 1, if the series is convergent, the corresponding sequence must tend to 0. Here the sequence is not tending to 0, therefore the series is not convergent. So now example 2, this represent the converse of this previous theorem is not true. So now we have a series 1 over n. The corresponding sequence is 1 over n. So the sequence has limit 0, but we shall show that this series is divergent. Why this series is divergent? Now let's see the sum of 2 power k terms. So this sum of 2 power k terms is greater than this number 1 plus k by 2 for all k. It means if you take a k however large, we can find a partial sum which is bigger than any k. So the partial sum sequence is not bounded above, although this sequence is monotonically increasing, but it is not bounded above, so it cannot converge. So if the sequence of partial sums is not convergent, therefore the series cannot converge, therefore this series is a divergent series. Now, theorem 2 is, suppose an greater than 0 for all n, then summation an converges if and only if Sn is bounded above. So this we already know from our previous chapter that if a sequence is the sequence is monotonically increasing and bounded above, then it is a convergent. And this series has positive terms. It means the partial sums sequence is monotonically increasing. Therefore, if that partial sum sequence is bounded above, only then this series can converge. Theorem 3, if mod an is a convergent series, then summation an also converges. Here we shall see in some examples the converse is not true. Sometimes summation an is convergent, but mod of an series is not convergent. But one side is always true. If summation mod an is convergent, then an also converges. Now, the main theorem of this lesson is the comparison test. So, test a given series by using the information of some other series that the given series is convergent or not. So, let's see what is this comparison test. Suppose an lies between 0 and bn for n greater than or equal to k for some k, then number one, the convergence of this bn, so Bn is bigger than An. So convergence of Bn implies the convergence of summation An. So if we already know that a series whose terms are bigger than the terms of this series, and this series is convergent, therefore this series is also convergent. So second is, suppose we know that An is divergent, then the series whose terms are bigger than the terms of An will also diverge. Some examples are summation n1 to infinity 1 over n plus 1 converges, because now this series can be written as 1 over n into n plus 1. So in our previous example, we have seen that this series is convergent, therefore this series is convergent. So in particular, 1 over n plus 1 square is convergent. So summation 1 over root n diverges, because 1 over n is less than or equal to 1 over root n. And we have seen in our previous page example that summation 1 over n is divergent. If summation 1 over n is divergent, therefore this is divergent. So example 3, summation 1 over n factorial is convergent, because n square is less than or equal to 1 over n factorial, and take their reciprocals, and we shall see that the convergence of 1 over n square will imply that convergence of this series. So it's clear that the comparison tests are very useful in determining whether a given series is convergent or not. Thank you very much.